here we are then, the culmination of, God knows, 2 months work. Whew, what a job. As you can see, these I mean, this is my finger for size. Yeah, this injector is around about 40 ounces a minute, which is 1.25 litres a minute, near enough. I'm actually going to put this back on the rig and test it. It turns out that the back pressure valve, which I was using a back pressure of 170 psi for a boiler pressure of 150. Now I kind of worked this out because, you know, friction in the pipes and raising the ball valves and all this. I wanted a 15% over, so that came out to 172.5, but you know, can't quite see that on the gauge, so I just went for 170. It turns out on the actual engine, when I measured it, as you saw, the back pressure was pretty much dead on. I assume once the injector lifts the balls, the momentum of the fluid actually makes it easier for the fluid to force into the boiler and keep the ball valve open. All the boiler's got is static pressure pushing on the ball, but the injector has dynamic pressure. So yeah, it turns out all I needed was 150 psi, but that extra 20 definitely paid dividends to have. It gives me not only more head, but it gives me easier starting, it gives me a wider range. So yeah, this is actually the design on CAD. Got a 13 degree included, and these are all included angles. 13 degree coming into the steam nozzle. This was from Dag Brown's. I actually needed 1.3 mil steam nozzle in the end. That was calculated using thermodynamics. And then I've got a flow straightener here. This isn't as long as maybe it could be. It's supposed to be 4 times the diameter, but I was opening it up slowly, making it longer, but then, you know, it was working, so don't fix it if it ain't broke kind of thing. I left it as it was. The land on the steam nozzle is maybe a little bit long, but it definitely aids in straightening, as you'll see on the test rig. Next we come to the combining cone. This ended up being 8 degrees. You can see I have chamfered the inlet slightly, but hardly anything. I mean, the actual nozzle is hardly chamfered at all. And then on every outlet I've done an absolute tiny radius, which stops any shear layer forming or reduces any shear layer. Now we come to the condensing cone. I've got the Linden Secret, as they call it, on here. All it is a slightly larger radius entering. It's just to stop any splashiness, because when the water and steam are mixing in this cone, it gets to the end of here, it's still not fully condensed, nor should it be, because it's still got this whole length to go before it condenses. It means that you're going to have steam which wants to expand as soon as it meets this area. This is the overflow 1 gap, which actually meets this hole here. When the injector's working, this is under vacuum, but it serves as a starting gap to allow steam to escape as the steam nozzle allows steam through here. Velocity increases. Velocity so high that it right at this edge, you're capturing something around 0.8 bar, which is 0.2 under atmospheric. That draws water in. As the steam hits the water, the steam condenses extremely rapidly, causing even more vacuum, which self-perpetuates the inlet. But yeah, there is still steam at this point, so it does want to expand, so this Linden Secret just helps capture that. The condensing cone is, as you can see, quite long. A lot of books that I've read, a lot of literature say that this entire section wants to be between 4 and 12 lengths of this diameter, which is the condensing outlet. So that's easily that. And at these high pressures, it really does need it. 150 psi really did need that length to get the steam condensed fully. Temperature I have on outlet is around 75 to 80 degrees, which via the maths shows that the steam is then fully condensed and the water's done its job. Next we come to the diffuser. As you can see, I've got a small 9-degree inlet taper. This is completely different to Dag Brown's big bell mouth entries. You can see there, it's absolutely microscopic once you get to this end. The water that I'll call it, because it's pretty much single phase. There's tiny pockets of steam at this point, but you know they've pretty much been condensed by now. And if they haven't, then they cause turbulence in here. So you want this length to ensure that steam is fully condensed before it enters this, because this is now compression. The water's moving at around 40 to 45 meters per second through this throat, which is only 0.82 millimeters. We then have a 3-stage diffuser, 5 degrees, 6 degrees, 13 degrees. Strickland and Nice, you know, they experiment with a radius, which for higher pressures should be up to 300 times this diameter. It's kind of difficult to make in the home workshop, so going with 3 diameters makes it easier. It creates stops boundary separation. You know, you don't want you want the fluid sticking to this wall and moving outwards. You don't want a jet coming out of here and just detaching from the wall. You want it sticking to the wall and slowing in speed gradually, so that you have a pressure front inside this nozzle, not inside this throat or in here, which when at slower water you can have, which I was getting a hell of a lot of overflow coming out of OV2 here, overflow 2, which is the second hole. As you can see, this is quite a different design, a lot longer, a lot sleeker. And this was the Dag Brown version. As you can see, he also uses annulus regulation. Nothing at all wrong with this. It just means that you are losing some of the condensing cone. You know, all of that from there to there is lost length, lost condensing potential. Also, trying to get this this bore lined up with this bore when you rotate it. Even if you clock, you know, you turn all this, that's all great. This bore is perfectly concentric to this, concentric to this. As soon as you flip it round, this is no longer concentric. Even with the 4-jaw, you know, you can clock in on this end, clock in here. It's still not going to be perfectly concentric with this bore. So, you know, this can be 0.01 millimeters offset, which does in fact cause the steam to exit at an angle, hits the water at an angle. We go like this, and when it comes out of this nozzle, it will be at an angle. Now this is why Dag Brown uses a larger radius bell mouth entry. It's because on these lower pressure injectors, the steam will be at as high a velocity, but the water coming out of here won't be. You know, you don't need as high a velocity to overcome the to beat the boiler pressure. And so not only is the jet not at such an angle, but the diffuser bell mouth can capture it easier. Now, why haven't I used a diffuser bell mouth? Well, as the water's exiting here, any gap between the water and the wall is actually causing a vacuum. So you're drawing air in here. And this causes, air entrainment. You're trying to compress a fluid, you're getting air entrained, it becomes less compressible, or it becomes more compressible, I should say. We don't want it to be able to be compressed. We want it to be raising in velocity, not compression. So when you have this lower velocity fluid exiting Dag Browns, it works perfectly fine. I've built one, and it worked perfectly fine on 120 psi, even up to 130. But after that, it just dies because it just doesn't have the velocity here moving into the diffuser. Also, the diffuser's at a 13-degree included angle, so for a faster moving jet through here, it will actually separate from this wall. A slower moving jet will allow itself to be attached to this wall and slow gradually. However, with 150 psi, that 30 psi makes such a difference. You can have more heat. You can have for the water to condense. It's still going to be moving at a similar. The steam's still going to be moving at a similar rate of knots as I've shown in the maths. Which, if anyone's interested, I can show. But I'm actually writing a book at the minute on all of this, how the maths designs the steam nozzle, and from that how you get the condensing lengths, and then how you need to size the diffuser nozzle. It's amazing to think that 1.25 litres of water can flow through a 0.8mm hole in a minute. But there we are. I suppose when it's moving at 45 metres a second, it will do. In summary then, when steam's on this end, it's very high pressure, very low velocity. As it moves down this cone, the velocity increases, pressure reduces until it hits the steam nozzle. This is where the steam will be doing Mach 1, so that's the speed of sound in steam, and this is called a choke nozzle. This means that nothing you change past this point will change the velocity through this nozzle. So nothing downstream, no extra water, no change in water temperature, no change in gaps, no difference in angles will change how fast the steam is moving through this nozzle. And that will be Mach 1, which is around 450 meters a second. Now that won't reduce your pressure enough to actually draw a vacuum at this point. You think you're at 150 psi at this end, which is what, 11.5 bar. By here, the maths says you're at around 6.5 bar. So you've halved in pressure, but you've dramatically increased the velocity. Now the flow straightener, this is what this does. It allows the steam to expand, raise velocity, and drop its pressure more. This means that, as I've said, at this point, right on this edge, the steam will be moving at around Mach 2 to Mach 2.5. That's 2.5 speed times the speed of sound in steam. And this is why you get just under atmospheric pressure at this point. That allows water to be dragged up or lifted into this what you call it, axial gap. And then, as obviously the steam hits this wall of water, it condenses extremely rapidly, causing a larger vacuum to be created. The combining cone does the initial job of combining that steam and water, so you're going to have water on the outside, steam jet on the inside, combining here. If you didn't have the condensing cone, you'd see a very hot jet of water and steam exiting here. The condensing cone then does the final condensation and also carries on raising the velocity, because the steam now is losing its velocity to the water, but the water obviously is taking up heat, and Newton's second law means momentum must be conserved, so the energy has to go somewhere, and that energy goes into speeding up the water. And by the time we get to the end here, the steam and water are balanced at around 45 meters a second. If you do the maths, 45 meters a second of a jet of 0. This exit here is 0.9 millimeters. Do the maths. That puts you somewhere in around 250 psi of head, which is outstanding, really. Which means that this diffuser doesn't really have to do too much work to recover that head, recover that static head into a dynamic head above boiler pressure. As I've said before, then the capture taper allows the vena contractor, as it is, to contract into this space without entraining too much air, which is compressible. We don't want compression, we want velocity. And the land here allows the vena contractor to stabilise before being re-expanded. As it expands, it slows down, and as it slows down, it re-raises in pressure until the end when it goes into the boiler. If you ever try one of these, be prepared to make some of the smallest tooling you've ever made in your life. These are D-bit reamers. This was a 0.78. This was a 0.8. And then this was a 1.3. You can find reamers online on a place like Cutwell, but they're going to charge you 30 quid a reamer for something like a 1.3. Even more expensive for a 0.8. So I got the Dremel on the lathe and made my own D-bit reamers, and yeah, done a really nice job. Also, you know, as experimentation goes, I made a hell of a lot of tapered reamers. I actually found that grinding old HSS drills is the way to go, rather than trying to turn ones like this. This is good for bigger ones, but when you get into the much smaller sizes, a HSS drill ground at an angle is far better, it's far superior. Else would be questioning on this is the steam nozzle, why I've got these holes surrounding it. Well, this disc is actually a water flow straightener or killer. Originally what was happening was water was entering here from one side and actually causing I don't know what else to call it other than turbulence, and a one-sided jet, which added to the steam being offset, and caused the jet to be coming out of the condensing nozzle at an angle. Now, although this angle was only probably 2 degrees, it was the best I could measure, that's still 2 degrees offset, so when it hits the diffuser, it's then bouncing off one wall more than the other, causing more turbulence, not allowing the water to stick to the walls nicely. So when I then upped the pressure, it was even more exacerbated. So what the water does now is it comes into the injector body around an annulus and into these two side holes. Now you think that these two side holes would then put the jet perfectly, you know, against the side of this, but no. I think what was happening, because it comes still from one side, the jets were coming in at an angle. And you can see the old hole there, but they were coming in at an angle and still causing, even after all this length, the jet coming out of here, because it was such high velocity, it was still at an angle, and you could see it when I had different diffuser geometries. You could see it coming out of one side of, you could see it sticking to one side of the wall there. So what I had to do was then add this flow straightener. So this then acts as a plenum chamber. So even if the water is coming in at an angle, it has to raise in pressure here, which then these 8 nozzles then direct the water square to the axis in 8 locations, and that has actually killed the angle completely. It's so important when pressing these nozzles in that you keep them perpendicular to the axis or perpendicular to the walls. Even though that is a this is a press fit in this bore, it can still press in at an angle and not be perpendicular if you know, if the tool you're pressing in with, if the face isn't perpendicular to the wall, or you know, or there's a bit of swarf under here, or you know, this isn't, the tube isn't square. It's it's plagued me the whole way through is squareness and keeping things axial. As you can see, pressing this in, this tool is actually a really nice close fit on. See, it's holding itself there. It's not a press fit. It's just gripping it enough so that, you know, I know that there's no axial play. So when I push this nozzle in, when I press this nozzle in to this shoulder, I know not only is that nozzle where it needs to be, but it's also exactly axial to the bore of this. What I'll often do is also give it a turn, make sure it's clean on the bottom, a bit more of a press in, give it another turn, and that just ensures that, you know, the tube is flush with the square block there, the precision block, and then I'll just push it home to the shoulder. Now I know as well as I can that that cone is square in the bore and square to the you know, the exact centre of the tube, which will hopefully allow the jet to be central too. To ensure the tool you're pressing in with doesn't have a completely flat face, look, it's got a hole in the face so that when I'm pressing in these cones, it's not going to interfere or, you know, cause a burr or push over the edge of that hole. I mean, that's 0.9 mil. It's absolutely tiny and easily be damaged. The next thing to note is the gap between these two cones. It's a little bit of experimentation, but you know, you can kind of logic out that at this scale it's not going to be a massive gap. You know, you're not going to have 2 mil gap, but you're also not going to have the gap needs to be big enough so that the initial steam can escape. I actually found that 0.8 mil is the perfect gap. You know, the CAD model can help you with this, kind of show you that, you know, somewhere between 1 and 0.6 the angles intersect, and the angle from the combining cone allows the water to into the condensing cone. So what I use is, I've got a 0.8 drill here, and that goes in there. As you can see, it's nowhere near yet, so I need to keep pressing it down until that just touches. To help me do this, I do use the Mills you know, quill feed here. And getting pretty close now. So what I'll do is I'll give it a small, and I'll give it another jiggle around. With doing this, you can easily overdo it and grip that drill piece. And gripping this drill piece means that this cone or this cone can now be off centre, because, you know, you've pressed, although this is pressing this square, you've now applied force to this bottom cone via one side with this drill piece. Be very careful when pushing these in. Eventually have to take these cones out, whether it be for cleaning or whatever. I've had to take them out today, obviously, for measurement, final checks and stuff. So just make marks, you know, where you can ensure that the alignment going back in was where it was before. That's marked, and the condensing cone's marked too. There we have it. The 0.8 drill barely go in there now, so I know that hole is or that gap, sorry, is just under 0.8, which was about perfect before. Unfortunately, there's no way to know whether you've got the cones in perfectly until you go on the test rig. Once again, when pressing into the bore, make sure that the alignment's correct. It's easier for me because I've got larger holes into the overflow channels, but your injector may have smaller channels, which means that that alignment really needs to be perfect. So before we start, a few notes on the boiler test rig here. This is an engine I made back in college. It's a two direction single cylinder. It's simple, but I hooked it up to a small water pump. I put I've got feed into the boiler. I can keep it topped up with water. I've actually rigged a gas burner, which I hook up here. It's a cross tube boiler, and when that flame's roaring, you can kind of hold your hand over the top here, so it's really efficient, effective. Water gauge, as you'll see, I do not have a safety relief valve. I could easily fit one here or here, but for testing boilers, you do not want your safety relief valve going off. Sorry, for testing injectors, you don't want your safety relief valve going off all the bloody time. It's just an absolute nightmare to keep track of. You just want to be able to build pressure, set to a range, and allow the injector to test. Now you could probably get a safety relief valve, maybe relieving up at 250 or something, but I tested this boiler up to 500 psi hydraulically, so I know it's good for at least 250, and I never even get it there via these tests. This is a 150 psi injector. The most I'm testing it up to is 170, so I've got loads of safety margin there. And I expect this thing could go up to 1000 psi easy, hydraulically, probably 500 psi with heat without splitting or anything. So yeah. So this is 5 minutes in now, 6 minutes, and we're up to 100 psi. As you can see, these valves are getting a bit old and knackered now. They're actually just ordered them from China as quickies. I was experimenting with an upgrade, but yeah, they've done the job so far. And yeah, as you can see, I'm not really going to give it more, but there's no need. We're up to 120, just about to test for the straightness of the jet. I do this just with a rule lined up with the body, and yeah, it's actually impressive how cohesive the jet that comes out of the combining cone is, really. So at 135, and to get the line primed, I usually just give it a little bit of steam now. I'll come up to 150. This is where the balancing happens. You want to be able to balance it, the flame, keeping it at 150, and the steam use, so that we can leave that and then test it. see is the jet is still straight, even with the diffuser in. And most importantly, with no load, the overflow 2 was dry, which means that that little 9-degree capture into the diffuser's working. So we'll just top off the water and then put the bottom bung on and see how she fares. So I've primed the line, I'm getting her up to 150, and then what I'll do is I'll start back pressuring and see what reading we get. Is just to hear how quiet it is. Oh my! Just so you can hear what the actual injector sounds like. It's absolutely quiet in operation. It draws the boiler pressure down quite quick, but that's the noise of it. Absolutely nothing. No chirping. Alright, we now need to top the boiler level up, so we've got the steam engine running. Nice and slow. Wait for the boiler to top up, I thought I'd say a bit more on the design cycle of this injector. While trying to design it, I went through about 120 design iterations. In the beginning I was trying to up the pressure of a fully working Dag Brown design. I realised after a while though that merely reducing the steam nozzle diameter wouldn't actually raise the pressure, as some might think it does. As we've seen, the steam nozzle is actually choked, it's at Mach 1. So reducing the diameter, all that actually does is reduce the mass flow of steam, i.e. the amount of steam passing through the nozzle. Obviously less steam means less power, but I didn't realise this until later on. Though as I tried to make the condensing cones and diffuser smaller to match the size of the steam nozzle. What I realised in the end was that the amount of water I want to be pumped in the boiler needs a certain amount of steam to raise its speed, and vice versa, the water condenses the steam to a required level of heat. You can actually use these values to calculate the size of the steam nozzle required for the amount of water you want pumped. And from there it's a case of calculating how long the steam will take to condense and the size of the condensing outlet. The condensing cone outlets then sets the speed of the water, the water is travelling. That's if all the water by then is condensed, and the angle of those cones are set by, hundreds of years of empirical evidence. Strickland and Nice do really good work on those angles. So once you have the condensing outlet, which in my case was 0.9, you then get a range of sizes to cut the diffuser inlet. From Strickland and Rees, they give a range, a ratio you can use to work out the diffuser. Mine ranged from 0.68mm to 0.9, which is helpful, but not that helpful. For instance, when zeroing in on the diameter, 0.76mm was too small and would create overflow because the vena contractor coming out of the condensing cone couldn't actually fit in there. But 0.84 was too big and the injector wouldn't actually create enough pressure. So you really can use the math to get you near, but unfortunately without modern CFD it requires a bit of guesswork and a lot of experimentation to finish the job. I think something else worth noting is how small the diffuser ends up for this pressure of injector. The diffuser throat is 0.82mm and I don't personally think I could make much smaller on my old Boxford. The accuracy just isn't in the machine anymore. I'm not sure how much smaller, say, a watchmaker can make an injector, but considering this one is 1.3 litres a minute, I think you'd be down at around 0.5 to 0.6 millimetres for, say, half a litre a minute. You could hardly see anything, and the smallest axial misalignment really ruins your day. Just think 0.01 millimetre axial offset, which can easily enter work. It's about 1.5% of the bore, and this can ruin performance. And there it is, fitted and ready for service. I've got the non-return valve there, which keeps the tube full, the delivery tube full, makes for easier starting. Yeah, what a result, eh? Beautiful.